This example problem illustrates how to calculate electric field from knowledge of the electric potential. So here's the problem. Let's say we know the electric potential as a function of x. Say some constant a divided by x plus some other constant b times x. And let's say that this is defined or known in some region of space where I've defined it like this so we don't have problems with x equals 0 location. So our task is to find the electric field in this region. Okay, so first let's review the integral derivative relationship between electric field and electric potential. On the one hand, the change in electric potential between 2 points in space is equal to the negative of the line integral of the electric field along some path between those 2 points. Here, ds is just a differential along the path of integration. Going back the other way, the x, y, and z components of the electric field are found by taking the negative of the derivative of the electric potential with respect to x, y, or z, as we see here. For those of you who have had Calc 3, we can identify this right here as simply the x, y, z representation of the gradient of the electric potential. So in general, we can write the electric field vector as the negative of the gradient of the electric potential. So if you've had Calc 3, this is a really nice compact representation that contains a lot of information. But if you haven't had Calculus 3, these relationships contain everything you need. Okay, so let's apply this to the problem at hand. We have the electric potential, the functional dependence of the electric potential, so all we have to do is take the derivatives with respect to x, y, and z and use them appropriately to find the electric field. So let's do that. Now, we note that this electric potential function has only x dependence. It has no y dependence or z dependence. So, the derivative of the electric potential with respect to y is 0, the derivative of the electric potential with respect to z is 0, and we're only left with this part right here. So we can plug in the functional dependence of the electric potential right here, take the derivative with respect to x, put all the other stuff in, and see what we get. And we can distribute this minus sign through to get our result. So, from this initial, knowing the electric potential as a function of x, we found the electric field as a function of x. All we've got to do to know the electric field at any value of x within this region is plug that value of x in here and we'd have the electric field. I'd like to wrap up with some brief comments on the relationship between the units of the electric potential and the electric field. The fact that we have an integral derivative relationship between electric potential and electric field means we've got a relationship between the units. So maybe it's simplest to look right here. The units of electric field are going to have to be the units of electric potential divided by the units for length. This tells us that the units of electric field can be expressed in the units of volts per meter. Now we already know that electric field can be expressed in terms of newtons per coulomb, but now we know that they can also be expressed in terms of volts per meter. And since all those quantities in there, newtons, coulombs, volts, meters, are all in the SI system, that means 1 newton per coulomb is equal to 1 volt per meter. And the volts per meter representation of the units can be very useful for conceptualizing what an electric field is, or giving an alternate conceptualization. So consider this. What we have here is that the electric field just gives us the rate in volts per meter that the electric potential is decreasing as we go along the electric field lines. That's a very useful way to think about electric field.